So let me give you two examples, two computational examples, where I feed the optimization with different style of sample. And the first one is the data points are extremely spread out, in the sense of it's just starts from -15 to +15 with the increment of 3. Right? In other words, you have data points, right, plotted here in these red dots that are separated by 3 times the standard deviation. And I insist to ask you to fit a mixture of Gaussians with 1 standard deviation. So if you run the program, and the results will be actually 11 component. So you will fit. So this blue is the fitted density. So indeed, it has 11 components, and the mode of this fitted mixture is very close to the observation that you'll see. So this actually, it somehow makes, I mean, in some sense, it's very reasonable. If somehow the data is so spread out, and you're tasked to fit a Gaussian mixture that best explain this, the best explanation is probably just to say each data point form its own cluster. Right? So this is known before, that if you have data of this form, it will fit a huge cluster and a huge mixture model. So this is a bad news, right? So this can actually happen. So this worst case happens essentially with positive probability. But the good news is that this sample is an atypical configuration. If your data is truly drawn from some mixture models, let's say IAD, the fact you observe these well spaced out situations is very unlikely, right? It can happen with some positive but low probability. So what is a typical configuration of points that you observe? So here is the same sample size, I think 11 as before. And then these are the samples I randomly drawn from, I think, a 2-component mixture of Gaussians. And then if you feed these numbers into the NPMLE solver, it will return to you two centers now. And then this is the center, and this is the weights. And the blue one is the fitted density. So in this case, it actually fits a 2-component mixture of Gaussian. It kind of reflects the observation of these red dots, and even if the sample is much bigger than 2 sample size, right? So okay, so this gives us some hope of proving this, and this is what people observe in practice already, and we're trying to explain this in theory as well. So let me do a bigger experiment. So here, this experiment is the following. I feed 10,000 sample to the NPMLE solver, drawn from a single Gaussian, just standard normal, right? So the optimization does not know the distribution is drawn from a single component. We try to fit infinite dimensional mixtures based on these 10,000 points. So I run this for 500 times. So number of the model size fitted by this is, of course, much smaller than 10,000, which is the worst case guarantee. It's usually around 10 or 11, right? So this is the observation that will be consistent with the theory. So it seems to be much smaller than n, right? Typically. So how to understand this? So the main results of this work trying to explain this, and the theorem is the following. So let me only explain what happens with Gaussian mixtures. So first, the first result is that it's actually possible to give upper bound on the number of atoms in the NPMLE solution using not just the sample size, but using the range of the data. So what we can show is that there is a universal constant such that the solution has no more than this constant factor times the maximum minus the minimum of the data points squared. If you think about these as the range, so this says the number of atoms will not exceed on the order of range squared, independent of sample size. Okay, so this is probably the most important and the most significant departure from previous results. So this sample size independent results allows us to conclude what happened when your data is drawn randomly. If your data is actually drawn from, let's say, a subgaussian distribution, right? So if, let's say, the mixing distribution is subgaussian, and you convolve with normal, it's still subgaussian. Thanks to the Gaussian tail, your maximum will be on the order of root log n, which is by union bound. And your minimum will also be on the order of negative root log n. So therefore, the range is on the order of root log n. So this tells you that with high probability, the model fitted by the infinite dimensional NPMLE will not exceed log n on the order. And so this explains this phenomena, that if you give the optimization 10,000 samples, it will typically fit a model of size roughly 10, or right, on this order, much smaller than that. So this significantly improves over the worst case results, that is n, and that is tight, because it focuses on the typical structure of the solution. So therefore, if your data is just a mixture of let's say 3 Gaussians or any finite number of components, you know that the range is on the order of root log n. So the number of points that this hugely over-parameterized solution will fit will not exceed log n. Right? So it's just a potentially very mild inflation of the model size. So this result is not just for Gaussians, it holds for a collection of exponential families with tail behaves as e to the minus x to some constant, and constant has to be strictly bigger than 1. So Gaussians, of course, one of them, and there are many more you can think about. And this result is more technical that I will not explain, and I will try to explain the reasoning behind this observation, and also the connection to the recent contribution of some information theorists. So the optimality of these results is that the log n is actually not possible to improve. So it's not possible to replace log n here by anything that is smaller order. And first, let me convince you that log n is the best model, is the correct model size, in the sense of it's sufficient to consider estimator with at most log n components, on the order of log n components. And this is just because you can actually approximate any mixture density where the mixing distribution is sub-Gaussian using log n number of components. So you can approximate the true distribution within total variation to 1 over n to the 100, and therefore you can simulate the data now. Right? So I can couple the n observations to a fake sample that drawn from a log n component mixture with high probability, right? So you cannot tell even if which one is a ground truth. So there is no statistical meaning to estimate a model with more than log n components. And indeed, for some reason, this non-parametric maximum likelihood will not go beyond log n. And also for the sake of accuracy, for the sake of convergence rate, it does not hurt to limit yourself to log n components. And the second thing is that log n is also necessary. And this relies on a negative result for approximation. So if you take the mixing distribution to be, let's say, normal 0, 1, in other words, the true distribution is normal 0, 2, and you try to fit a mixture with unit variance, right? And if your number of components is k, the best approximation will not be bigger than exponential in k. But we also know from existing statistical guarantees that NPMLE is close in root n accuracy, close to root n accuracy. So this says just because of the bias, right? Your k has to be at least log n to be compatible with existing statistical guarantees. So you know that log n is necessary as well. So therefore, from these two perspective, we conclude that log n is the right model complexity, and somehow without any regularization, this NPMLE self-regularizes and automatically chooses the right model complexity. So this is, I think, the most surprising results of this research is that you could get away without any regularization. And this is the slides that I promised earlier to Salim's question. What people usually do is to penalize the model size, right? You try to constrain yourself to KGM with K components. And this is some non-convex problem that you have to somehow solve. So maybe you run the EM heuristics. And then you try to determine there's upper bound of the size of the model you want to tolerate. And you choose the one when you include the fitted likelihood, right? And then penalize by the growing of the penalty, for instance, log K, on the order of log K, let's say. Or sorry, on the order of K. So then what the new result says that this function, which is random, but as a function of K, with high probability actually plateaus after your model size exceeds log n. So it's a bit counterintuitive. I mean, usually when you feed a bigger and bigger model, you have a higher and higher likelihood, but somehow with high probability, typically this curve just becomes flat. Right? So that's it's equivalent restatement of the theorem. So this is the reason that somehow in hindsight, this completely unpenalized, unregularized MLE works. Of course, if you penalize it, it works too. But the problem is it's not easy. It's not so easy to compute.
So Yihong, so just
yes, please.
So this is not a property because you mentioned the overfitting, and I want your view on this because I don't understand completely. But there is more the algorithm picks. You have many local minima because it's non-convex, right? And then the SGD or whatever picks the good local minima that has self-regularization. But here, it's not a property of the algorithm, right? It's
right. So this is a good point. So here, what happened is that I have convexified my solution space to the entire convex call, right? So I might pick some very complicated solution, but due to certain behavior of the gradient, so this whose mode tells you where the solution is, driven by the random data, it somehow only have a small number of modes. I think maybe that's the better way to put it. So therefore, yeah. So I will show you this interpretation in this form. So this is not about a non-convex optimization. Does gradient descent reach a good, statistically good local maxima? So here the problem is completely convexified. So you are fitting some model which could be much more complicated than your ground truth, but somehow it won't happen. So, but if you insist on classical model selection consistency, in the sense of if the true distribution has 3 components, I want my fitted model to have 3 components with high probability. So I don't think NPMLE can achieve that. And as you observed before in this experiment, the true data has a single component. It will fit maybe 9 or 10. So, but I think this is just a mild overfitting. So there is a very small price that you paid, which is logarithmic, in order to be completely automatic. Right? I do not even need you to tell me how many components there are in practice, in reality. But if for consistency, you definitely need to know this. Right? So let me speed out a little bit. So let me skip this slide, I think. So there is some other NPMLE which is known to have these properties in shape-constrained literature. So I will skip this. But I think the point I want to make here, let's say, is that these results are thanks to explicit characterization of the solution. Whereas here we only have this KKT condition style of tail-biting equation, so it's much more difficult. And the statistical consequence I'll mention briefly is that you can prove what has been shown before, the density estimation guarantee for the NPMLE using this self-regularization property, because this essentially tells you that the problem can be reduced to a finite Gaussian mixture model with log n components at most, right? Because somehow this solution restricts itself to log n components, and you can also approximate ground truth with log n components. So essentially, you have an effective dimension of the problem, which is only order of log n, right? And the rule of thumb in statistics is always says the effective number of parameters divided by sample size, with maybe some extra logs. So you can recover these results, which was previously shown by Zhang, very simply at the high level, using this self-regularizing property. So I'll skip this. So let me give you a warm up, and then I'll explain the proof. I think that maybe that will be the end of the talk. So it turns out that although it seems it was not noticed before in the literature, but you can prove the self-regularizing property in Poisson mixtures very easily. Just 2 lines. So the Poisson mixture is exactly as before. I have the Poisson mean parameter theta. Then I try to fit a convex combination of a number of Poisson with different means. Right. So this is the Poisson density. And the important observation is that the Poisson is discrete distribution. So the observation takes values in non-negative integers. So if you just write down the gradient as before, right? So this gradient has the very special structure, is exponential times a polynomial. So there's nothing magical here, just plugging in the Poisson density. But the important observation is because these samples are discrete, right? So they are integers. So a lot of them, if you draw n Poisson random variables, a lot of them is going to coincide, because the maximum is only on the order of log n, right? Or even smaller, maybe log n over log n. So in other words, because these xn's start to collide with each other, this, although it's a sum of n terms, in reality, it's only of degree. That is the maximum of x. Right. So this is a very low degree polynomial times exponential. So if you take the derivative, it's also exponential times the same degree polynomial. And I know a degree polynomial of degree, let's say d, at most d roots. Right. So therefore, when you fit a Poisson mixture, right, even if you have n observations, your number of roots here is at most the maximum of your observations, which usually grows very, very slowly. If you have a nice mixing distribution, Poisson is going to have exponential tail, so the maximum is only order of log n. So this immediately tells you that without any new techniques, you can prove Poisson model and running NPMLE on Poisson model will return to your model of size log n with high probability. And log n is also the right model complexity for the class of Poissons. So of course, this doesn't work for Gaussians, because for Gaussians, if xi's are truly drawn from a Gaussian density or mixture of Gaussian density, it's going to be distinct. Therefore, this sum is generally going to have n distinct terms. They're not going to be combined into a low degree polynomial. And they are not polynomial anyways. So there are some new techniques that is needed for analyzing such situations. So let me explain this. So remember before, because of the first order optimality condition, I already know that the solution is going to be supported on the set of critical points of this gradient. Of course, the gradient here is defined itself using the optimal condition. So it's not very tractable to think about how does these weights behave. But I know the form, right? The form is, as I mentioned, just a superposition of n Gaussians with centered at the data points, and with some mysterious weights, which I cannot get a hold of. but it's fine. So it's of the form of a Gaussian convolution, right? It's a Gaussian convolution with some measure supported on the data. Essentially, it's a reweighted version of the empirical distribution, which is hard to describe, but it's supported between x min and x max, right? Convolved with the normal density. So if I have a technology to count the critical points of a Gaussian convolved with compactly supported distribution, then I can apply this result here to conclude the number of critical points of the gradient. And so that's the starting point. Is try to understand the number of maximas of Gaussian mixtures convolved with the compactly supported distribution, not just with not fixed number of components anymore. Right? So here's the main results. The results is that if you take any distribution, right? So this distribution could have a density, but it's confined between plus minus a. And you convolve with the normal, how many modes can you create? So you might think that if you have plus minus a, right? And I take some huge separation, let's say 100, right? Then it looks like I can create on the order of a maxima. But it turns out that you can do better. You can create a square. And a square is tight. You cannot create more than a square. So this is the results that immediately proves the main results announced a few slides ago, that the square of the range bounds the number of atoms in the solution. So this result actually was first shown very recently in the independent work of Distel, Yagli, Poor, and Shamai in analyzing, believe it or not, the amplitude constrained Gaussian channel capacity. For that purpose, remember, there's a classical result due to Smith that proved the solution is discrete. Distel et al. Want to understand how many atoms are actually in the capacity achieving input distribution. And they proved this lemma for their purpose. So, and this is the same lemma that we use in our paper as well. And although they showed up in some unrelated context, this is the main observation underlies the theory, at least for the Gaussian model. And the lower bound, that the A square is tight, was proved independently by Navin Kishab and his co-authors, and also in our paper. So in fact, this equally spaced construction that I mentioned, you can actually make the spacing 1 over a instead of a huge constant, and still creates many different modes. And this requires a more difficult analysis. In our paper, I'll give a simpler to prove sinusoids construction. So I think this explains this. So in the remaining 3 minutes, I will give you a quick proof of these results, how to bound the number of critical points of a function, of a nice function. So that's the starting point, using complex analysis. So the main observation is the following. I want to understand the behavior of the derivative of a Gaussian mixture, which is a very nice analytic function. So first, let me go to complex plane. I'm going to want to analyze overbound the number of complex zeros. So here's the results that relates number of zeros to the integral of a function. So if you take a very nice analytic function and you integrate over a circle of radius r, center as 0, what you're integrating is the log of the modulus of the function. And the average, subtract the log modulus of this function at the center, is related to the following integral of the number of zeros. So this is identity. So where nt is the number of complex zeros inside a disk of radius t. Okay. So therefore, if I can have some handle on the size of G on a big circle of radius r, right? So let's say suppose g of z is less than some m for all z less than r or equal to r, then I can upper bound it by log of m, value at 0. I can lower bound this just by integrating not from 0, but from some r. Right? So it's from some r. Just drop part of the integral. And this tells me it's number of zeros times log of the ratio of the radius. So I can use, so what does this tells us is that I can use the information of a function on a bigger circle to control number of zeros in a smaller circle. So that's summarized here. And that's what happened when you apply this to this mixture of Gaussians. So to implement this recipe requires essentially 3 things, right? First, I need to localize the roots, because these results can only allow me to control number of roots inside a disk. So I need to know where the roots are. So that's number 1. Number 2 is I need to have some control over the value of the function at some point from below. And the third thing, I need to control it from above on a huge circle. Right? So then that will complete the proof. So this can be done easily here for mixture of Gaussians. So if I have a mixture of Gaussians, a Gaussian convolution, right? So let me use for convenience some random variable u. Let's think about this as the input variable, right? And then I add some noise and I look at its density. So that's just a convolution in this form. So the first observation is that because u takes values between plus minus a, all the real roots, all the critical points of P, of the output density, is confined in this interval 2. And this is just because if you take derivative of the Gaussians, you get this, and this is between plus minus a. So if x exceeds a or smaller than minus a, is going to be either positive or negative. Right? So all the oscillations happen between plus minus a. I only need to bound the number of roots in a radius between plus minus a. Then I go to the complex plane. I bound how many roots in a complex disk that enclose this. The second thing is I need to pick a point, right? So what happens here is that I know all the roots is here, plus minus a. I pick some point here, which I can say something about the value from below. Then I choose a circle of this radius r that enclose all of this. That will allow me to count how many real zeros in total. Right? If I pick outside this interval, I have some good handle on this value. And Gaussians is e to the minus a square order. And then you can also upper bound it from above, because Gaussian, the growth at the most e to the quadratic. So when you combine all of this, you get a square. So the proof for exponential family is more complicated. I will explain, but I think this is a self-contained exposition, and the paper of Disto et al. Use a similar technology. So I think this is I will just maybe conclude with the last slide. That's yes. So I think this showed some. Yeah, I don't know why it doesn't work anymore. Yeah. So the conclusion is that this work showed some surprising self-regularizing property of this hugely over-parameterized maximum likelihood, despite the absence of any penalty. So this happened in some mixture models. For instance, the most prominent example is Gaussian mixtures. But also there are some limitations. I don't know why. To this result is that it doesn't, for instance, include mixture of exponentials. So it's a simple tweak. The results, the current proof technique, give you some useless results. And also, what happens if you introduce a little bit of constraint to the program? Does it achieve a better self-regularization? Also, I didn't explain this in details, but essentially people know very little about this in just dimension 2, as opposed to dimension 1, believe it or not. So let alone high dimensions. So there's a vacuum in understanding theoretically and also computationally, right, how to actually compute these solutions in 2 or 3 dimensions. You can discretize, but it doesn't scale. And also, I didn't explain this, the NPMLE plays a very prominent role in empirical Bayes. And the theoretical understanding about this approach is a nice open problem. So the paper about the results I mentioned, and also this discussion about this open problem are in this archive preprint. Okay, I stop here. Thank you so much.
Thanks a lot, Yihong. This was very interesting. So we have time for maybe 1 or 2 questions. If anyone has questions, feel free to unmute yourself and ask the question. Maybe I can start if people are shy. In 2 dimensions, because you showed some interesting simulations or numerical results where when you picked from single Gaussian and you ran the
right.
Do you think have you like tried for not a single dimension?
Right. So there's a huge distinction the moment you move away from 1 dimension. For instance, what we know just very recently is that the solutions with positive probability is not even unique. But it seems it's unique with high probability. So that's the difficult thing.
But do you think you observe the same kind of concentration of, I don't know, like the low kind of?
So the mode characterization is true. So the gradient condition I described in the beginning, that is contained in the critical points of this gradient, which itself is a mixture of Gaussians, is dimension independent. It's still true. But if you go down that route, you're going to run into difficulties, because I mentioned if you have a superposition of n Gaussians in 1 dimension, you can at most create n modes. Right? So that's how people prove the classical results of n atoms. But if you have n Gaussians in d dimensions, the number of modes you can create is the only order of n to the d. So you can create a lot more modes in 2 dimensions. You can create n square modes. So it's not an easy construction, but you can somehow create n square modes. So you cannot use these results now to prove, for instance, uniqueness anymore. But this is a very bad configuration that probably won't arise in when your data is random. But even the classical theory, due to this fact, already stopped working.
Okay. Thanks a lot, Yihong.
Thank you so much. I mean, if any questions, feel free to send me an email.
Okay. Thank you, everyone.
Okay. Take care, everyone. Yeah.
Take care. Have a nice weekend.
Thank you.
Bye.